Hi, this is part of a series of videos about differential equations, and in this video we're going to look at a couple simple applications of differential equations. That is, a couple of kinds of situations that we can model with fairly simple differential equations that we can then go ahead and solve. So first of all, suppose you have a hot cup of coffee. Where do you think it would cool the fastest? Sitting out at room temperature? Or if you put it in the refrigerator? Well, seems obvious that it would cool faster in the cold refrigerator than out in the room temperature room. And that's because there's a bigger difference between the temperature of the coffee and the temperature of its surroundings when it's in the fridge than when it's just sitting out on a desk or a table. And so it seems reasonable to assume that the rate of change of temperature of an object, that is, how fast it cools down, is proportional to the difference in temperature between the object and its surroundings. If it's already the same temperature as its surroundings, it's not going to change temperature at all. If it's very close to its surroundings, it's going to change a little bit, fairly slowly, to cool down to reach the same temperature as the surroundings. If it's much hotter than the surroundings, it's going to cool way down pretty fast. And if it's colder than its surroundings, its temperature is going to rise. It's going to get hotter until it reaches the temperature of its surroundings. So to model this with a differential equation, I'm going to use T to stand for time. And then, since I've already used the letter T to stand for time, I can't use T for temperature. So let me go one letter ahead and use U for temperature. So U is going to be a function of T. U is going to be the dependent variable that depends on T. So U of T represents the temperature of the cup of coffee at time T, which is left in a room where the temperature is a constant 20 degrees Celsius. I could do temperatures in Celsius or Fahrenheit or Kelvin, but we'll just do Celsius. So to say that the change in temperature is proportional to the difference in temperature between the object and the surroundings, that means that du dt, the change in U with respect to T, or the change in temperature with respect to time, would be equal to some constant times the temperature of the coffee minus the temperature of the surroundings. So here U minus 20, the 20, it might be some different number, but it's whatever constant temperature the surroundings are. And the U is the temperature of the cup of coffee, or the object that is changing, cooling off. And because it is cooling off, its temperature is decreasing. So that's why I stuck a minus in here. The change in temperature is negative because the temperature in the situation we're picturing here is decreasing. Okay, so there's our differential equation. Du dt equals negative k times U minus 20. Let's solve that. That is a separable differential equation, so I can separate the variables. I can multiply both sides by dt, and then divide both sides by the expression U minus 20. Then integrate both sides. So on the left side, the integral of 1 over U minus 20 du is the natural log of the absolute value of U minus 20. Now, if we're assuming that U starts out being more than 20, we're talking about a cup of coffee that is initially hotter than the surrounding room temperature, then U minus 20 is going to be positive, and we don't need to mess around with the absolute value. But if U were less than 20, we could still do this, and then the absolute value bars would be important. On the other side, the integral of negative k dt is negative k times t plus a constant of integration c. Now let's get the ln out of the way by exponentiating both sides. E to the ln would just be U minus 20, and then on the other side we've got e to the negative kt plus c, which breaks up into e to the negative kt times e to the c. But if c is any constant, e to the c is just some constant, and it would have to be positive, but if the absolute value is equal to some positive constant, u minus 20 itself could be a positive or a negative constant. So we'll just write u minus 20 equals c times e to the negative kt, add 20 to both sides, and u equals 20 plus c e to the negative kt. So there's the function, that the equation that tells how u depends on t. This is sometimes referred to as Newton's law of cooling. The initial temperature, the temperature that you start at time t equals 0, would be 20 plus c times e to the 0. That is just 20 plus c. So that means that the number c here is the difference between what temperature the coffee starts at and what temperature the room is. So if originally the coffee is, say, 50 degrees hotter than the room, C would be 50. And the initial temperature of the coffee itself would be 70 degrees, 50 degrees hotter than 20. And the other constant in here, the K, depends on sort of what the thing that's cooling down is made of. If it's a cup of coffee, is it in a nice insulated styrofoam cup or some other kind of mug? That's going to make a difference in how fast it cools off. So that number K depends on what it is that's cooling off. Some things cool faster than others, and it can be determined if we also know the temperature of the coffee after some other number of minutes besides 0. And notice that if we take this expression and take the limit as t approaches infinity, so we're letting the cup of coffee just sit there indefinitely, as t approaches infinity, e to the negative kt, so that's going to be like 1 over e to the positive kt, that would be approaching 0, and so the limit would just be 20. So in the long run, the coffee is going to approach the same temperature as the room that it's sitting in. Suppose, for example, if you want to look at some specific numbers, suppose the coffee is initially 90 degrees Celsius, and then 5 minutes later, it's cooled down to where it's 70 degrees Celsius. That means u of t is going to be 20 plus 70, and here this 70 is the difference between the 90 degrees that the coffee starts out at and the 20 degrees that the room is. Remember, the C here is the initial difference in temperature, how much hotter the coffee is than the room temperature. So u of t in this case would be 20 plus 70 times e to the negative kt. If you stuck a 0 in for t, you'd get 20 plus 70 times 1. You'd get 90 degrees. And if we also know that when t is 5, sorry, that should be a 5 there, u of 5 equals 20 plus 70 times e to the negative k times 5, that's 70 degrees. We can then subtract 20 from both sides, divide both sides by 70, take natural logarithms of both sides, and divide both sides by negative 5 to get the value for k. Here it comes out to be the ln of 5/7 divided by negative 5, which is approximately 0.067. So here's what the specific function would be in that situation, and here's what the graph looks like. The coffee starts out at 90 degrees, and over time it cools off and approaches 20 degrees. So after 60 minutes, the temperature of the coffee is just a little bit above the temperature of the room that it's sitting in. Okay, second application. Imagine something that spreads from person to person. It might be an infectious viral disease. It might be a rumor or a piece of gossip or a piece of news. It might be some new piece of technology that people see somebody else using and they got to get one too. So over time, that viral infection or that piece of gossip spreads from person to person to person How fast is it spreading? Well, that depends at any given moment on how many people are already infected and also on how many people are uninfected. If nobody's uninfected, it can't spread at all because there's nobody for it to spread to. So we could assume that the rate of change of the number or the percentage of people infected would be proportional to the number of people who are currently infected. More people who are infected, the faster they can spread it to others, and also proportional to the number of people who are not infected. The more people who are not currently infected, the more people there are who could become infected. So that gives us the differential equation dx dt equals k times x times 100 minus x. Here I'm using t for time as my independent variable, and then x depends on t. X stands for the number of people who are infected, or if you prefer, the percentage of people. And you could imagine a situation where there are 100 people in the universe, like maybe a class with 100 kids in it, or a small town with 100 people living there. Or you could just think of 100 as standing for the maximum percentage of people who could be infected. If x is close to either 0 or 100, the rate of change of x, the spread of the infection, is going to be close to 0. But if you're somewhere in the middle, like right around 50% infection, then it's going to be spreading a lot more rapidly. So let's solve this differential equation. It's also a separable differential equation. So we can separate it out into a function of x times dx equals something times dt, and then integrate both sides. And to integrate something like 1 over x times 100 minus x, we want to take that fractional expression and split it up into two separate, simpler fractions. So this involves what's sometimes called partial fraction decomposition. This is equal to some number over x plus some number over 100 minus x. Multiply both sides by the common denominator, x times 100 minus x, and we get that 1 equals a times 100 minus x plus b times x. And this is supposed to be true in general for any particular number x. So if we plug in 0 for x, we get that 1 equals a times 100 plus b times 0. That is just 100a equals 1, so a equals 1 over 100. If we plug in 100 for x, we get 1 equals a times 0 plus b times 100. So b would also equal 1/100th. That tells us what these numbers are. So that tells us how to break up the original fraction into simpler pieces that are easier to integrate. So when we integrate, we get 1/100th times the ln of x minus 1/100th times the ln of 100 minus x. And I'm assuming that x has to be somewhere between 0 and 100 so that these things that we're taking the ln of are both positive. That way I don't have to mess around with absolute value bars. And that's equal to kt plus c. I can multiply both sides by 100. I can convert ln of x minus ln of 100 minus x into ln of x over 100 minus x. And then undo the ln with e. E to the ln is just x over 100 minus x, and that's equal to e to the 100 kt plus 100 c, which is e to the 100 kt times a constant. Now, taking this equation and solving it for x, well, first let's suppose one person is infected to begin with at time t equals 0. Then we get that c must equal 1 over 99. Then we can solve for x and get x equals this expression here, or we could take this fractional expression and divide the numerator and denominator each by e to the 100 kt and make it look like this. So k is some particular number. If we put in 1/100th, these are the numbers we get, and this is what the graph looks like. And this is an example of what's called logistic growth. This is a logistic growth model.